All right, so welcome back. So now that we've looked at the root test and the ratio test, we now want to apply them to the idea that we introduced in the previous section, which was that idea of absolute and conditional convergence. Remember, the idea is simply this. If we have an infinite series, uh, if the sum of the absolute value of the terms converges, we say it converges absolutely. And of course, an immediate consequence of that is if it does, the series of the absolute values terms does converge, then so will the other series, whether it's alternating or weird series or whatever. However, if the absolute value diverges, yet the series where we allow negative signs in converges, then we say that that's conditional convergence. And of course, if the alternating or whatever other kind of series diverges, then automatically the more restrictive, where everything has to be positive, will also diverge. We actually saw two quick examples of this, the two categories of convergence, right? 1 over k, the harmonic series diverges, yet the alternating harmonic series, as we saw from the alternating series test, does converge. And so this is a situation where you're dealing with conditional convergence. And then in the other example, 1 over k squared, the p series converges. And of course, by the alternating series test, so does the alternating series. This is an absolute convergence. Absolute convergence. Okay, so that's what we're looking for. And of course, the third possibility, does it just diverge? Like, for example, this series minus 1 to the k, right? That's just going to diverge, right? That's just going to diverge, right? Because the underlying series obviously diverges, and by the alternating series test, the limit of the k goes to infinity. Of course, that also the alternating series also diverges. So that would be an example of one that diverges, like minus 1, again to the k. That's going to be a series that diverges. Okay, so, but if it does converge, is it converging absolutely, or is it converging conditionally? And again, that's talking about these two different types of scenarios. So that's the idea that we're ready to address here. Determine if the series converges absolutely, conditionally, or if it diverges. Okay. So let's consider an example here. Let's consider the sum as k goes from 1 to infinity of minus 1 to the k factorial divided by k to the 6th. Okay. There's different ways to approach this series here. I'm going to approach it just to review my ratio and root test type things, just to kind of look at that and approach it from that point of view, and then we'll go from there. But you could actually try some other test here, but I think I just want to use the root test, or not the root test, the ratio test here, because I have that factorial in there. So you could do some other tests, but I'm going to look at the root test. So I'm going to take the absolute value, so it's going to drop the sign. That means I'll be dealing with the series k goes from 1 to infinity of k factorial over k to the 6th. Okay, so I do my limit as k goes to infinity, and that will be k plus 1 factorial over k plus 1 to the 6th power, and then it'll be over k factorial times k to the 6th. All right, and we simplify here. Limit k goes to infinity. Remember, k plus 1 factorial k plus 1 factorial is going to be k plus 1 times k factorial, right? And then that k plus 1 to the 6th is going to be in the bottom. It'll be sitting down there in the bottom, right? And then the k factorial will stay in the bottom, and the k to the 6th will come up top. Okay, and so we can do a little bit of simplifying here. So the k factorial cancels out. Notice that also the k plus 1, the 1k plus 1 in the top, will cancel with one of those ones in the bottom. So that in the end, we have a limit as k goes to infinity of k to the 6th over k plus 1 to the 5th power, which we could really just think of as k to the 5th. There's going to be a bunch of other stuff, but k to the 5th is going to dominate. K to the 6th over k to the 5th is k. So the top is growing faster than the bottom. So therefore, this is going to infinity. So therefore, the absolute value sequence diverges. Okay. And then we look at the alternating series. So this diverges. So what's going on with the alternating series? Well, for the alternating series, remember, we first look at the limit of the underlying sequence. Okay, that's kind of the first idea with the alternating series. So the limit as k goes to infinity of k factorial over k to the 6th. And we immediately see that there's a problem here. All right, we immediately see that there's a really, really big problem with this. For it to converge by the alternating series test, it would need to go to 0. But once we get beyond k equals 6, this thing is going to, this k factorial is going to start dominating stuff, right, like crazy, right? That's going to become a bigger and bigger degree polynomial. So, of course, that's going to outperform something like k to the 6th. And so this is going to go to infinity. So, therefore, it also diverges. The alternating series also diverges. Now, I chose to do the root test here to test the convergence. I chose to do the, not root test, the ratio test to test convergence here. We also could have used this same reasoning with the divergence test, right? Since for the absolute one, we could have looked at that and used the same reasoning. Hey, that goes to infinity. So, of course, it doesn't go to 0, so it's going to diverge. So we could have gotten the full-blown one from the divergence test, just like we're looking at that underlying sequence for the alternating series. But I just wanted to review the root test. Right, I keep saying root test, the ratio test, because that is always a good thing. When you see factorials, the ratio test is something to always look for. So I just wanted to review that. That's partly why I chose to do it. But this one could have been done by looking just at the divergence test first. So overall, it diverges both ways. So we say that the series diverges. Right? So the series diverges.